All right. There is a notion of time. So time is t equal to 1 to capital T. All right. At time t, you have to choose an action. Let's call it x of t. The information available to choose xt is f1, f2, whatever here, f3, so until f of t minus 1. One step behind. You got to choose xt depending on all the past information available with you. All right. What is the objective? Essentially, to minimize summation of ft of xt, t going from 1 through capital T. Unconstrained for the moment. I'll put some constraints in a minute. Okay. That's the simplest setup you can think of. So you're evaluating your action at a function which is not even revealed to you. Should look hopeless, but we'll soon see things are not that bad. And for the time being, it should look hopeless. It's as if I'm trying to optimize a function I don't even know. Okay. Now, what is the benchmark? There are two types of benchmarks. We'll only consider one today. One is static optimal. Other is dynamic optimal. In static optimal, you get to see all these functions f1 through f capital T ahead of time, but you can only choose one action across time. Single action. So x will not depend on t. It will be a single action. So let's call it x star is equal to r min x summation fi, let's call it t, x, no xt, t going from 1 through capital T. So that's your static benchmark. You're allowed to choose single action, but looking at all f's ahead of time. Here, you're allowed to choose actions, but you're only allowed to see the prior functions. Dynamic optimal is nothing but essentially xt is equal to xt star. You get to see the function, there is nothing better. You would simply play xt star, where xt star is argmin of precise function ft of x. So you want to compare what you are going to get with respect to a static benchmark as well as a dynamic benchmark. So try to even understand, does it even appears reasonable what I'm trying to do?
The second one.
Here? No, so
equals to t to 1 y 1 to t minus 1.
No, because I get to see all. I get to see all the functions. So the best action at time t is a local optimizer. I cannot do anything better than that, right, at time t. Why is this not clear? So here, if suppose the information structure was that all f's are known to you at time t,
Yes.
for little time t, what would be your xt? Xt would be simply xt star. You cannot do better than that, right? Something is missing in the definition. Tell me what is missing. I'll correct that.
No, I have some basic doubt.
Yes.
So at each time when you are getting a looking at the previous information, our new information at time T is getting better, or it can vary also.
This is all. Now getting better,
Yeah,
worse, I can't say.
Yeah.
All I'm saying is at time t, I know all the past functions.
Yes.
What is better and worse? I'm getting more information. Information is getting accumulated. You can choose to ignore it, you can choose to use it.
Yeah, if I was supposed to choose the XT star, simply.
How will you choose xt star? You don't get to see ft. You get to see f1 through ft minus 1. This is only for the dynamic optimal. This is not, you cannot beat this. Your algorithm cannot get here. This is only a benchmark. This is a static benchmark. This is a dynamic benchmark. Static is choose a single action across all time, looking at all f's. This is choosing optimal actions at each time t. Any other question?
In static optimal, the summation will be up to t or t minus 1.
T, right? Why t minus 1?
Because we don't know t, ft, right?
For static optimal, f1 through f capital T is revealed to you ahead of time.
Okay.
All you're doing is selecting one action. So that's why there is no T dependency here. Single action X. Okay. So I give you, so we'll take an example just to clarify things. So can you come close to either of them? This is only harder. Can you even come close to this is the question. You are playing blind. So when I say come close, so let's say static optimal. That is how much? Let's call it X star. So this is ft of X star. So this is what you are going to incur. This is what static optimal is going to incur. X star is nothing but argument of that. So I'm just evaluating all the FTs at X star. So what do you think should happen? Is it reasonable metric, unreasonable metric? You can take the difference of the two, you can take the ratio of the two, whatever you want. It's multiple ways in which you can look at the performance gap. You can take the subtraction, it's called regret. Take the ratio, it's called competitive ratio. Doesn't matter. That's not important. What is important is this quantity, can you find some way in which to choose xt such that it's not too large compared? What would be trivial? A trivial algorithm, which is bad. Okay, what would be the, let's say, the difference of these two quantities? If you randomly choose, at each time you disregard f1 through ft minus 1 also. So let's make a simple assumption that each xt has to belong to chi, which is bounded, and f's are also bounded. So ft, just by definition, ft also. ft is convex. So each time you have to choose an action, it has to belong to chi. Chi is bounded, and ft over chi is also bounded. Choose whatever bound you want. Now, if you do a random strategy, what will be your answer? It should look like capital T times something. This is sum over capital T times slots. So the difference here is bounded by choosing a random answer. You will essentially get capital T times some bound. So that's a trivial algorithm. Question is, can you do better than that? That's really the challenge. Under this information structure, can you do sublinear in T? Let's put it more concretely. Capital T. Because linear in T is easy. Any arbitrary algorithm will be the difference between these two terms will be growing linearly in capital T. Is that clear? That capital T is trivial? So, is there any hope of bringing it down? So, formally, this quantity is defined as regret or static regret is equal to minimum over, or rather, let's remove the minimum here for an algorithm. So, ft of c minus ft of x star. So this is the cost of my algorithm, any algorithm I'm running, and you maximize this with respect to the choice of f1 through f. Because I don't have this under control. Somebody can provide me in such a way that this whole thing is quite large. So that's why there is a maximum over all function choices, which satisfy these properties. All f's are convex, all f's are bounded. This is the cost of my algorithm. This is the cost of the static optimal. Yes?
Yes. Have you done any similar thing in the class before?
No?
Uh,
Why should I?
As I remember that there was a problem where you wanted to look at some minimizing some sum AIT. That you started with that you made the constant C. First, you make the sum to a constant C, and you wanted to do a argument for achieving C. What can be the bound on the parameters?
No, this is nothing similar to that. You're not realizing the difficulty of the problem. Your action xt is being chosen without knowing f of t while I'm evaluating it on that. That's the non-triviality of the problem. Earlier, we never seen any such setting. We at least knew a function to optimize and did whatever we wanted to do. Iterative method, non-iterative method, whatever. Here, the problem is somewhat different. I'm not even telling you what ft is. I'm asking you to choose an action and then saying, okay, here is the loss you incurred on that function. Choose the next one and go on. And comparing it to a static optimal, which knew the functions ahead of time, but was allowed to choose only one action. So let's take an example just to clarify things. Sorry?
Bounded convex function will have the maximal at the boundary.
Maximum, minimum, right? You want minimum.
Right.
So we are minimizing a convex function. So think of, let's say, f1 equal to f3 equal to f5. So all the odd ones to be equal to x square. So all odd functions are this. And all even functions are let's say x minus theta whole square. All right. So what does it look like? So all the, this is 0. This is my theta. Let's take a different color over here and let's write. Okay. So these are my f1, f3, and so on. And this is my f2, f4, and so on. So what is static optimal? What is my x star? Should be theta by 2, just by symmetry. What was theta x star? Arg min x star was summation ft of x t going from to capital T. Does everybody agree x star is theta by 2? Capital T is even. Okay. Otherwise, you will say no, no. So capital T is even number. So it better be that this is my static optimum. Now think about an algorithm which at time 0 starts somewhere. Right. So it's sitting somewhere. It doesn't get to see f1. So it can't change anything. So it just stays there. So x1 is also equal to x0. x2, what should it do? It gets to see this blue curve. Then it should be clear to everybody. X1 is some number. X1 is equal to x0. Because I don't get to see anything, there's no need to change. I have no idea what. So without loss of generality, let's say x1 is x0. Now you get to see f1. You already lost on f1 of x0. That much you have incurred, you can't do anything. So what you have not taken care of? So no control over f1 of x1. You have no control. Now you get to see f1 before you choose x2. What should you do? Which will be reasonable.
Up to 5 minutes.
That's a good algorithm. But something more simpler. You get to see the full f1.
For your extra 2 theta by 2, it should be even, right?
If you don't pay attention to that, I can't do much. Yeah, go on. What other algorithm you can think of? That's also one candidate. Something even more simpler. Which post facto, if this is what you're going to see, somehow what do you want? You want your algorithm to converge here, right? What algorithm do you think is simple enough which will converge for this particular example? Don't even worry about other arbitrary f1s and f. So if I, for the moment, you know what these f1s or f2s are. Come up with an algorithm which is online, that it uses only the information of the previous step and converges towards theta by 2.
So xn is the argument of summation e from 1 by 1.
Right? That's what your algorithm is. Oh, one candidate. Anything else? X. Once you give me more candidates, I'll tell you why this makes sense, what is it trying to do, and why it doesn't work. Actually, it doesn't work for some reason. It should work, but it doesn't. It's a good algorithm. What else could you do? Something simpler. You're saying something like this, right? Xt is equal to argmin of ft minus 1 itself. That's another candidate online. Just looks at the most recent one and just does it. And what's surrogate for this? Surrogate for this is xt is equal to gradient descent on ft minus 1. This is finding exactly. Here I'm just doing one step gradient descent with whatever step size I want. So wherever I was, so xt will be xt minus 1 minus eta gradient of ft minus 1 xt. That's try to see what does this algorithm do for this input. The third one. So this is number 2. If this works, 2 should better work. Eventually we'll analyze this one. 1 is kind of different. Okay, so now think of on this input, does it converge or not? So prove by example for the moment. We'll do the rigorous proof pretty soon. So what will happen? What will be the first iterate? You're starting at x1. What will be x2? Take eta equal to 1, let's say. Which direction will you point out? I'm not looking for precise answer. All you have to justify is that it moves towards theta by 2. That's all you have to justify. So what will happen at time 2? Which direction will I go? Is the question clear? Because the answer is relatively straightforward. So that's why I'm surprised. Is the question clear? You're starting at x1. You're following gradient descent. What will the iterates look like? I don't want precise ones. Just give me the direction is sufficient.
Okay.
So at this point, the gradient of f1 is, so this is my x1. It's quite large. What is the sign? We'll try to push it towards essentially 0. So we'll take some step like this. Step number 1. Essentially, I'm moving in x direction. Now what will happen? Suppose I reach here, let's say. This is my x2. Now this guy is very high. Right? At this point, it has gone beyond the board. I can't even see. So what will it try to do? We'll try to push it even further down. So again, this will move a lot towards x3. Now this is very large. We'll try to come down. So this will keep pushing me. And if I choose eta appropriately, this won't have these wild swings, but we'll try to try slower and slower towards theta by 2. Is this picture clear? Most important is the picture here. Rest of the proof is actually 2 lines. And you don't get, or rather, I never have satisfaction that I'm done. The proof is correct. It's 2-line proof. The basic idea is this, that why it actually works. So if I choose eta roughly 1 by square root t, it will depend on t. These oscillations will be smaller and smaller around the optimum. Basic idea is this. And this is one of the worst cases you can think of for this algorithm, where every function is just alternating between good and bad for that particular point. Is that point clear? Why the input I have created is actually one of the bad sequences of inputs for any algorithm. So what is it doing? It has opposite behavior for optimal. Wherever you are, you're trying to push towards 0. Wherever you are, you're trying to push towards theta. There is no overlap between the consecutive ones. If one of the red ones are actually, so rather than taking f1, f3, f5, I could took f1, f2 to be equal to x square, f3, f4 is equal to x minus theta whole square. It will only make my job easier, because consecutively I'm trying to optimize the same function. Here, I'm alternating between the two. I can choose theta whatever, however large I want. So theta is not important. This alternating behavior of trying to optimize two opposing functions essentially makes the job hard. But even then, it's not too bad. So it should not only give you a sense that this algorithm should work, but also it should work for any possible function. Because the input I'm showing you is one of the worst possible inputs you could create in this setting. So whatever answer we're going to give will be independent of f's. It won't depend on if f's are nice or f's come in a particular order, we'll get an answer. We'll give an answer universally for all possible f's as long as they're bounded over a bounded set. All right, so that's your is called online gradient descent. This is somewhat more complicated. This is called follow the leader algorithm. So what is it trying to do? It's as if trying to say that whatever information I have so far, this is what static OPT would have used if only that many functions are available. It's looking at all possible functions seen so far, trying to essentially do what a static optimal will do and trying to replicate that. So that's called follow the leader algorithm. The problem with this is, hopefully I will have time to show what the problem with this algorithm is. It swings a lot, and that's where, so the subsequent iterates you get, they tend to have this behavior of swinging a lot. So xt will be small, xt1 plus possibly will be very large. Again, xt plus 2 might be small, xt plus 3 might be large. So there is a fix to this, which is called the follow the regularized leader. So you add a regularization and you fix it. I'll briefly give the idea at that. Okay, so are we set for proving online gradient descent? Is the problem clear? That's the most important thing. Performance metric should be clear. We are after the regret, which is defined to be this quantity. Our goal is to show that somehow this is order sublinear in T. Linear in T is trivial. Okay, so what's the guess for what order we'll get? Many guesses from this example or anything you think about? 1 by root T. That would be too small, right? You're saying regret or define after regret? So one way to say it is regret divided by T. Are you saying regret divided by T is 1 by square root T? Or regret itself is 1 by square root T? What we are going to attempt is to show that this is theta of square root T. We'll show upper bound, and I'll leave as an exercise how to show it as a lower bound also. That there exists a choice of functions for which you cannot do better than square root T. What I will show is an upper bound for the gradient descent algorithm. Okay, the proof will be rather trivial. It won't be satisfying because we'll see why it works, it works. Okay, so theorem online gradient descent as regret So xt will be the actions taken by online gradient descent, and x star will be a static optimal. So just by using the convexity of ft, what can you bound this quantity by? The most basic definition of convexity. This is less than equal to gradient of ft at what? At xt minus x star. What should the argument be? X star? Really? Or xt? This is our basic convexity definition. The signs have been switched. That's why it has gone to xt. Okay. So in the regret, if you remember, this is the quantity I want to control, summed over all time t's, right? ft of xt of my action minus ft of x star. But by convexity, this is already bounded by this. So if somehow I can bound this quantity multiplied by xt minus x star, I should be able to control the overall. Okay. So what is, any idea how to control this? Remember, what is my algorithm? xt is equal to xt minus 1 minus eta t. I'm making step size dependent on t, most general. You can always do this, ft of. That's my update rule. Online gradient descent. At time t, look at the gradient of function ft minus 1 and make one step. So using this, how do you think I can control this quantity? All I want is the control over the right hand side.
If we replace the gradient by the objects,
Yes.
minus 1.
Okay, what will I get? We'll get xt minus 1 minus xt divided by eta t.
Yes.
Okay.
Multiplied by the xt minus
Yeah, okay.
So
Hmm.
those so we can think about those are.
But look at what is getting multiplied. It's ft of xt, right?
Yeah, so that is xt plus 1 minus xt
Okay.
by
So,
xt plus 1.
so these terms will be off. That's what I'm trying to indicate to you. So you'll get whatever from there, but what is getting multiplied? Xt minus x star. So you won't get a norm and all correctly. If you were to attempt that, you won't get much. But what are you after? You're after xt minus x star. So that should give you some idea. You've been doing this forever. So what is xt minus x star mod square? This is by this definition. Xt minus 1 minus eta t gradient ft of xt minus 1 minus x star. Just by definition, right? And why am I interested in this? Because look at this quantity. When I take the square, what kind of terms will pop up? There will be a xt minus 1 minus x star multiplied with the gradient term, the cross term. There will be exactly that term. Rest will be xt minus x star square, which is somewhat similarly here, only with a different index. And there will be a gradient square term. Now, gradient we are going to assume bounded, which will be ft minus 1.
No,
Ft minus 1.
You have replaced xt by.
Yes.
Yeah, so ft minus 1 in this case.
Yes. So now if you open this, what will you get? You will get first term as just combining this and this minus 2 times eta t gradient f of t minus 1 x of t minus 1 xt minus 1 minus x star and plus 2 times eta t del f t. So far so good? Okay. So now tell me, everything is on the board now. Remember, this has to be summed over all times. So if you could somehow exploit the telescopicity of anything here, that would help. So what is telescopic? This is xt minus x star. This is xt minus 1 minus x star. So it's staring in your face. How should I combine things? I wanted control over this thing, so I'm just going to move that around. So 2 eta t del ft of xt minus 1 xt minus 1 minus x star is at most, it's actually equality. So I have to do that is equal to xt minus 1 x star minus xt minus x star plus 2 eta t. Let's call it some g square, an upper bound on the gradient of all functions. That I need to know. And that's why I'm going to put a upper bound on this. Sorry? Sorry, one at a time. Eta square? Yes, eta square. 2 is not there? Yes, 2 is not there. Where is ft minus 1? Here. Okay. There are too many indices.
In the last box.
Okay, so what have we achieved so far? We've been able to upper bound this quantity, which is exactly what I wanted without the 2 eta t. So one eta t will disappear from here and the first term will have eta t in the denominator. Now can you just give me one step in which I can finish the proof? What is telescopic about it? There's something telescopic there.
Whatever G square.
G square is fixed. G is just an upper bound on the gradient of all functions over the full domain.
One thing. So if we just take a mod, we cannot take a mod, but that term, so those are two vectors, right? Basically.
Which vectors?
The gradient and xt minus.
Yes.
Yeah, those are two vectors, right?
Yeah.
So that will be upper bounded by the norm of.
But I don't need it, right? Just look at it. I've already upper bounded it. Why do I need to do further upper bound? I have been able to upper bound the inner product itself. Now all you have to do is to just sum it across time. Because if you look at the right hand side, there is a telescopic sum. Lots of terms will actually get cancelled off. All you will get is just two terms. The first one and the last one. That's what the advantage of all this is. If somehow I was adding all the capital T terms, this will blow up linearly as capital T. But just stare at this for a second. All I'm going to do is to add across time slots t equal to 1 through capital T. Just the subsequent ones will all cancel out. The first one will remain and the last one will remain. And that is constant. Essentially the diameter of the set X or set chi. So summing over, equal to 1 to capital T, you get ft of xt minus ft of x star summed over is at most equal to how much? See, you'll get a eta square, or let me remove the eta so that there is a single eta t. Eta t, t going from 1 through capital T, that's my second term, times g square from here. Here, once I divide the eta t from here, that will also disappear. One eta t will remain. And on the second term, what will I get? 1 by eta t. Can you say what exactly it will be?
X1 minus x square minus x2 minus x square.
Sorry.
H1 log of x square x square.
So long form, can I write this eta t 30 minus 1 xt minus x star whole square, summed it over t going from 1 through capital T. That's what you will essentially get. What are these terms? Xt minus 1 minus x star minus xt minus x star. And what am I replacing it with? See, the first term will be no, lots of them will cancel out, right? Which ones will cancel out?
The first term.
Because I'm adding across all time t. See, the tth term here gets divided by 1 by eta t. So the next one will be eta t plus 1. So that is why you end up getting this. So now this is nothing but diameter square, and this guy cancels out to be at most d square times 1 by eta capital T. This is just straightforward because of the minus. The first term will be with a minus, I can just forget about it. And plus summation eta t, t going from 1 through capital T G square. Sorry?
G is also dependent.
No, G we have, what we are assuming here is for all functions across all time, the gradient is upper bounded. The gradient square is upper bounded by G. That's an assumption we're making. So you take the max of all if each of them are different. Okay, so now what is the only thing remaining to choose is eta t. What should be my eta t to balance the two out? See, one is in the numerator and adding, one is sitting in the denominator. So if I choose eta t equal to 1 by square root t, is it sufficient first of all? If I do that, I can do better, but if I do this, will the two terms have the same order? This will be capital square root t, that's clear. What is the integral square root t? So what is integral 1 by square root t? That will upper bound this quantity. So this will be d square times root t plus g square times root t. That's what it will look like. But I could do better than this. I could throw in d's and g's also if I knew. So what should I do? I'll just simply say gd times. That's correct. Yeah. So eta t equal to what is this writing? D over g root t. So I'll also get rid of the d squares and the g squares. So I'll end up getting, this is not required, this is at most, g times d times. So this g and d essentially are constants is what we are assuming. And that's why we are interested in looking at the square root t order of increase. So the proof, I'm pretty sure, does not illuminate anything. So that's why, as a takeaway, remember this example, that why it actually works. The proof is rather too elementary to reveal anything for itself. Should really think of it as chasing the previous optimizer. That's the way I think about it. That this algorithm is trying to chase the previous optimizer. See, what is this one step doing? It's trying to move towards the optimizer of the ft minus 1. And that's in some sense a right thing to do. So the same proof will work for this also. Because when you are doing exactly, because you can always do better than this. So now a lower bound. Why do you think square root t cannot be beaten? Or at least try to think. Once you have something like this, the obvious question is, can you do better than square root t? Can you do constant, for example? So for that, you'll have to construct a set of functions for which you cannot do better than square root, no matter what an algorithm you run. So it has to be an algorithm independent lower bound. So what's the obvious choice?
In the same function, square root.
Sorry? The example I gave. See, in this direction, there are typically two choices. One is an input which is difficult to predict. Two is it's too corner case. It's like very bad in some sense, depending on the algorithm. Sorry? No, those functions. That's not what I'm trying to say. See, what matters is not the function choice itself. How it is changing is what matters here. If you give me one function, however bad it is, that's not going to give you a bad input here.
You're saying that in the
The
previous
sequence is what matters.
So in the previous example, I had shown that the sequence is oscillated in this event.
Yeah.
So you wanted to create a sequence where it should follow something. It will update itself by root t or something.
That's too much to ask for. Every time someone will jump by square root t. All we are saying is the regret across capital T time slots is roughly square root T. And that we already shown. So you can't create an example where it is larger than that. So think of a sequence which is difficult to predict, right? That's what we should really think about. If you could predict the sequence, you would do as close to the static optimum. So what's a sequence which is difficult to predict? An IID sequence. An independently generated sequence. So what is the most obvious choice for that? The simplest choice of an IID generated convex function sequence. What's the simplest convex function? Don't say constant. Sorry? No. Something simpler. Linear function. So between x square and constant lies the linear. So think of a linear function where it's like some a trans or C transpose x where C transpose is the vector is just uniformly random. What do you think is going to happen? So that's my function. F1 is C1 transpose x, F2 is C2 transpose x, where C1, C2, C3 are all IID. I've not given you the distribution. What do you think is going to happen? So let our set phi be x and Rn. So that infinity log is less than 1. All right. Everybody understands it. Right? Max is less. Okay. What is my function going to be? So take v to be plus minus 1 to the n. What does it mean? N length vector which takes value plus minus 1. How many possible choices do I have? 2 power n. So this is choose ft is equal to ft of x is equal to vt dot x, where vt is IID uniform from v. All right, makes sense? With probability 1 by 2 power n, any one vector is chosen. That's my function. Now, what do you think is going to happen? Now, I've completely specified the input, and each time I'm just picking uniformly randomly this vt from this set, multiplying by x. That's what is given to you. Two things. One is, what is the loss you are going to incur for your algorithm, whatever that algorithm is. So that is ft of xt. And what is the lost minimum ft x going? That's the loss the static optimizer is going to incur. At least tell me, see, this is all random. So just tell me whatever your algorithm is, what is this quantity equal to? Remember, the algorithm doesn't get to see VT. It only sees the previous ones. And given that it is entirely random, you're going to choose an XT. What does this look like? Expected value of summation VT XT. And what is VT? VT is uniform distribution over all possible binary vectors. So what is this quantity, irrespective of what you do? Is everybody certain that this is 0? Okay, so this is what you can achieve. Now think about what the static optimal can achieve. So this I leave as an exercise. This you should be able to show. This is minus precisely n times square of t. You can take it order. That's how much you can make this static optimal. So this is a question mark for you. Do it later in your free time. It's not one step. You have to think a little bit why this is true. Some inequalities involved here. But that's the order how much you can reduce it by. So this gives you a lower bound that no algorithm should be able to do better than square root t regret. Don't have any question? This is clear? I'm not proven it. All I'm showing you for this input, static OPT can get you minus n times square root t, while you cannot do better than 0. So the difference is exactly how much you have shown our upper bound. Question? Your question?
Think about this example. Is the vertices are important of the polytope?
No. What did we do? This is true for as long as the expected value is 0 for whatever distribution you take, this should be okay. For this, it is important that it is taken to be an n length vector with plus minus ones. You will see, essentially, you will try to see how will you choose an x, right? Because if you choose one bad x, it will, you're not allowed to change it over time. So if it gets aligned with some of them, it will get misaligned with some others. So that's what you have to worry about. That I have to make this alignment in such a way that I get this much. Is it always possible or not? Understand what this means, right? VTs are revealed to you, but they're still uniformly random. So if you choose an x, which is putting a -1 wherever there is a +1, at some places you will get a hit and some places you will get a miss. You would like all of them to be minuses because that's what you're trying to do. But once you fix a minus, you'll also get multiplied with another minus, which is coming from BT itself. See, x is what you're choosing once. So x is the n length vector you're going to choose for yourself, depending on whatever you're going to see. So let's say some place you choose a -1. You would like lots of these VTs to be +1 there, so that you get a contribution of -1. Similarly, if you choose a +1 at some place, you would like at those places to be -1. But there will be some places where it will be +1, and you can't avoid that. So question is, there is always a choice, knowing what it is, that you can get it n times square root t. That's the question. All right. So as usual, we first do for convex functions, then we go back to our strongly convex functions. So far, nothing changes for a strongly convex function. So now think about, if ft is strongly convex, I want to improve this inequality from square root t to log of t. How can I do it? So this is always true for convex function. Something more is true for a strongly convex function. I've not used that here. All I've done is I've just upper bounded this quantity. So if I, in addition, if I give you that ft is strongly convex, what can you change here? This bound is as it is. This is not going to get touched. So this plus something. What is that plus something? Yeah, let's take beta. Okay. How will you use that is the question. So for a strongly convex, function. What do we have? F of ft of xt minus ft of x star is less than equal to del ft xt minus x star plus beta over 2 xt minus x star whole square, or minus there. See, I've already shifted the sign, so be careful. I'm looking at a less than equal to inequality. Typically in convexity, we're looking at a greater than equal to inequality. So it should be a minus there. Okay. And I already have that upper bound on this quantity. Give me the trick to go from square root t to log t. Hopefully, in your notes, so there is some bound on this, right? What was that bound? Let me just rewrite here. Del ft of xt minus x star is equal to mod of, just make sure I don't make a mistake here, xt minus 1 minus star divided by 2 eta plus eta by 2 g square. Is this t minus 1 here, or was that correct? It is t minus 1 first. So t minus 1 here. Very good. Okay. So now I have additional in this part. How do I exploit that? So all these are also eta keys. So when this term was absent, all I could do was possibly, I got 1 by eta capital T plus summation of 1 by, summation eta T itself. I chose eta T equal to 1 by square root T and balanced out the two terms. Now because of that additional minus, what am I getting? When I took the telescopic sum, which terms survived in xt minus 1 minus x star and xt minus x star? The first and the last, really. And only the one with the positive sign actually survives, right? But what is this contribution is going to be? The minus thing. That is also true for every t, right? So when I add, this will add as it is. So what choice of eta t, I can get rid of the first term entirely. That's all you have to think. Is there exists a choice of eta t for which I don't get anything in terms of xt minus 1 minus x star? Because then I can choose eta t independently of, I don't have to choose bad choice of 1 by square root t. I can choose something like 1 by t itself.
One thing. So to get that log term, yeah, so if I get a harmonic split,
Yeah.
1 by t.
Yes, that's what I want. How do, yeah, that will do. But just go back to how did we go? How did we get to square root t? What did we end up getting? D square times 1 by eta capital T and this summation of eta t's. So suppose I chose eta t equal to minus 1 by t itself, not 1 by square root t. What order would I get here? It will be simply just 1 by t, right? It will just go back and become linear in t. So if I chose my step size to be 1 by t, I would get an order t regret. The first term will be dominating. This will be very small, but this will dominate. This choice was made so that both of them are balanced. But suppose if this term didn't even exist, then I can choose 1 by t here and make it logarithmic. I could actually make it as large as I want. But to make this disappear, I have to choose something. What is the choice here? Eta equal to how much? 2 is not important. So suppose I chose this. What would happen? See, this is going to get added for all time slots. So these guys are anyway cancelling. Lots of them are cancelling. But there is an additional beta by 2 sitting from the outside. So as long as eta t is this, why do you think it's cancelled off? So let's just sum it over all times. So summing it over all times, you get ft of xt minus ft of x star is less than equal to summation t going from 1 through capital T xt minus x star multiplied by 1 by eta t minus 1 over eta t minus 1 minus a beta and plus our usual g square times eta t. So this is the addition compared to the previous step. That's all we really have. Every single term has exactly this. Don't worry about 2's and okay. So this was not there when functions are only convex. So now why does choosing this eliminate this term completely? I'm claiming that this is actually less than equal to 0. I can forget about this and all I have to worry about this one. Sorry?
Beta t minus beta t minus 1.
Beta, there's just minus beta there. There's no t.
After putting the value. After putting the value to be only beta minus beta.
This one?
That will be beta t and for the next one it is beta into t minus 1.
Yes.
So beta t will be cancelled the beta.
So all you will get is essentially beta minus beta. So this actually goes away. And all you get is this much. And then summed over 1 by t, all you end up getting is g square times. When functions are strongly convex, the step size is much smaller. But also depends on the strong convexity parameter. And ends up giving you a regret which is order wise. So much better. Square root t and log t, there's no comparison. So, yeah, you can prove it for yourself that you cannot do better than log t. No matter what happens. That's up to you. All right. So far so good. Any questions? So what's the essential difference between convex and strongly convex is? Essentially, this term helps you to reduce the step size and get rid of the first term entirely. And this can be controlled better with 1 by t rather than 1 by square root t. All right. So now let's look at so this is all I will say about the online gradient design. Essentially, there is this much only known for this particular problem. For dynamic regret, it's a completely different ballgame. So now let's look at the follow the leader algorithm. What is XT? XT is argmin summation fk of x, k going from 1 to 3 minus 1. Okay, so now want to control the regret. What shall we do? So can you come up with an instance where things, rather, the decisions made by this algorithm are abruptly changing? Whereas for an optimal algorithm, it would not. So that doesn't actually mean that the regret is bad. All I'm trying to indicate is, can you create an input for which xt and xt plus 1 and xt plus 2, they're just oscillating wildly. And there is no step size here also.
So in the previous example, we took odd function for x square meaning function just square. If we just add some for with each of them, if we just add a one value continue, just to make the parabolas in the shifted parabolas basically.
What is n?
So the odd for 2n.
What is n? N is the number.
Yeah.
Okay.
So the if 2n is basically x square plus n, and if 2n minus 1 is basically x minus theta square plus n.
Yeah, why would it shift?
So basically the
Look at the algorithm. Yeah, it's adding all the functions and trying to find one minimizer for all the functions seen so far. The input you're creating won't have that behavior. Because what is the major effect? As time progresses, the major effect is already contained there. The new function coming in is not going to change it a lot. See, in here, what you have to do is to, every time a new function comes in, when you get updated, suddenly it has to change, which is kind of weird. You would not expect that to happen. You would think that sufficient mass has already appeared. It should not give you any reason to move away from that optimizer. It should move slowly, but it's not necessarily true. So think of what kind of function there will be where every time a new function comes in, the optimizer changes. It doesn't change in small amount, changes in a lot.
parabolas.
It won't. Think about it.
That's conjugated one.
Yes.
Like whose center is at 0, 1 and 2 and 3. When you so at time t, it will be somewhere lying between 1 to t.
Yeah.
But when t plus 1 comes, the point will move from 0 to in between some mass within 0 t plus 1.
Think beyond it. Think of the following example. Ft is equal to Zt times x. Okay. And x, our set is just minus 1, 1. One dimension. Okay. What is Zt? takes three possible values. Minus half at t equal to 1. 1 when t is even, and minus 1 when t greater than 1 odd. Okay. Function is clear? Now tell me what xt's are going to be for your algorithm and what you would have liked. It is just simply subtract plus ones and minus one, whatever you accumulated so far. It's meaningless. Every time you see something new, you jump. Is clear? Because it's plus one. So a lot of time has disappeared, right? At time t, what is the effect of all these additions? The plus ones and the minus ones will all disappear. What will matter is the most recent one. What you get? You won't get at time t, the t minus 1th guy. And that will either be plus, so it will try to do a minus 1. If it's minus 1, it will try to do a plus 1. So xt will keep oscillating between plus 1 and minus 1. But supposing you knew all of them ahead of time, what x would you have played? Static optimal?
0.
Trivially 0. Right? Because single answer, half of them are plus ones, half of them are minus ones. The best answer you can play is 0. So this algorithm, this is the problem with this algorithm. That even though it doesn't appear it should happen, but it does happen. And that too with linear functions. So what is the fix to this? The fix to this is, instead of doing this, you add a regularizer which stops it from jumping around from time step to time step. So you do the same thing. You add a regularizer which won't allow it to change too frequently. And that is your xt. So the regularization will dampen its effect of moving between consecutive steps. So this will be an increasing function, typically convex or strongly convex. What k? Should it depend on k or not? So give me a reason for it to depend on k.
The example that was created,
Yeah.
they thought that particular it should not be dependent on k, but if there is.
What am I trying to control? That consecutive steps should not change too much. So why should it matter what k is? All is going to control is from wherever I'm starting, from point A to point B, what is the new addition? The new addition is just one function, right? Every time a new function comes in, this gets recomputed. I'm adding a regularizer to control that. It should not oscillate like this. So let's look at an example where something happens, something very interesting happens. Let's say if t of x is some b times x, linear function. Let's call it vt transpose. And the regularizer is simply x square by 2 eta. All right. What do you think is going to happen magically? What is my follow the regularized ladder? X star is arg min summation vk transpose x, k going from 1 through t plus x square divided by 2 eta. What is x star? resolution minus, or let's call it +1. I have a t here. Can you write xt plus 1 star in terms of xt star? This is the simplest possible optimization. Even if you don't want to just guess it. See, xt star will be solving one less, that's all.
The difference between the T star square and T star.
What is the solution of this? Let's do it the brute force way. What will this look like? Argmin.
xt plus 1 star is xt plus 2 eta vt minus.
Okay. What is the answer here? We'll come back to that. What is the argmin of this quantity?
Minus 2 eta summation vt.
Summation.
Sum of vt.
K going from 1 through t. But how can I write this in terms of xt star? So 2 should disappear according to notes. Because when you take the derivative, 2 will disappear. So there should be no 2. Do people see why this is true? Nothing but a derivative, that's all. This is true. So if this is true, the t, if I remove the tth term, what will I get? xt star. So this is equal to xt star of minus eta vt. So there should be a minus here. Just there is a minus sitting outside. So if I count it towards t minus 1, that will give me xt star and an extra minus eta times vt. Look at the function, look at the update. What are you reminded of? So FTRL for linear functions with quadratic regularizer is nothing but OGD. So OGD is a special case for a particular type of functions. So with the regularizer, you should expect to get back the same guarantee as OGD, and you actually do it. Okay. Proof is slightly longer, but the basic idea should be clear that why regularizer helps is because it tries to dampen something like this. It doesn't allow it to change arbitrarily. So on this example, you should go back home and try to see if you put a quadratic regularizer, what is going to happen. Why it won't allow you to swing. All right, so let's stop here.